My name is Scott Drummons. I am a recent addition to EMC's VCE partnership and the vSpecialist team. But when this talk was submitted, I was a VMware employee. So today I'll be talking as if I continue to be a VMware employee. Before we get into that, though, Dave and I have some prizes we're going to give out. We're going to do a little Q&A to warm up the audience. These questions will tell you just a little bit about each of us, some personal stuff. I went to a school in southeast Alabama called Auburn University. And I'm a big fan of the Auburn Tigers. And so my first question to everyone is, and I will accept the answer, the first person to shout it out, who was the last winner of the Heisman Trophy from Auburn University? Oh, wait, who was that?
Right there.
Right there, okay. We have for you a extra large Zimbra t-shirt. Where was it, over here? There you go, thank you very much. Oh, sorry about that. And one last question, also of the Auburn trivia sort. And this one's a bit subjective, but I think we'll all agree once you hear the question. Who is the most well-known NBA player from Auburn? I think I heard Charles Barkley first over here. Very good. Sir Charles Barkley. Both of these guys, unfortunately, I never got to see play. But Bo Jackson was such an idol that his face was on everything at Auburn. He owned all the restaurants. His jerseys were everywhere. Too bad we couldn't see more of him in the NFL. Dave.
Yeah, so if you've been to any of the sessions, you've seen that the VMware employees are wearing the black polo shirts. So I went to the speaker room yesterday, got my shirt in the morning, went back to my hotel, and busted out the iron and did a real good job getting it all ready and put it on, and realized they had given me a women's extra small. And the sleeves were here and the waist was here. So I chose not to wear that one, for better or for worse. But they did give me one of these. So being from Winnipeg, Canada, I will ask the trivia question. What is the name of the former pro hockey team out of Winnipeg?
I think it was way in the back there. Yeah, no, it was like a back row almost. Yeah. Perfect. Winnipeg Jets.
Represent.
So, with that, I thank you all for coming very much. We appreciate this. Dave and I have been presenting on and off a variety of topics now for several years. We met actually in both of our very first project at VMware, which was an exchange solution work that was done with EMC's commercial solution teams about 4 years ago. And we have been colleagues and friends ever since, and we'll hear some more about that as we go into the talk. First, standard boilerplate. This really does not apply to this talk. We have nothing forward-looking. Yeah?
It's a beautiful slide, though.
Thank you. What we're going to talk about, what this session is about today, is we're going to give you guys a little bit of a historical narrative about the last 4 years of application performance and some of the changes that have occurred in VMware as well as in the hardware itself. And we're going to lead up to application data that is very much brand new. And I hope that a bit of this summary will give you a background, a little bit about how VMware works, tell you a little bit about maximizing applications, and also give you ideas of the variety of applications that are out there and why it is that a growing percentage of them can actually perform better on top of VMware than they can in a physical environment. So first, what's the background? Well, when I started in 2007, I had transferred over from a performance team in Intel. And when Dave and I were sent out on that very first project, he as the storage expert and myself as the performance expert, it was very much an open question if Microsoft Exchange would run correctly on top of VMware. At the time we were dealing with ESX30, and there had never been that I know of any white papers that qualified the overheads and the response time of Exchange. We know now, after years of analysis, that Exchange is a very intensive workload, but we didn't know if we could virtualize it within acceptable boundaries. Acceptable, we used to define back in those days as about a 30% loss of throughput. I don't know if you all consider that acceptable or not. I think by today's standards, no one would find that acceptable. But back then, that was a position where we felt reasonably we could sell all the goodness of VI3 and people would buy it if they only lost 30% of the application. And I did not know, I don't think anyone knew, if we could get Exchange inside that boundary. So by the time we got to 2009, so many changes had happened in the industry. VMware had done so much work around its platform. Of course, the name change to vSphere was, I think, a great sign that things had radically changed, especially in the performance world, that it became possible to virtualize really about 100% of these workloads. So, and what are these workloads? Well, the sample we're going to show you today is a wide one. It really touches, I believe, 5 very, very different applications and talks about some of the technologies that makes faster than native possible. So first, let's look at the historical aspect. I said in 3.0 back in 2007 that it was really a challenge to virtualize Tier 1 applications. This is one of the decks we used for the 3.5 launch when we were talking to people about how the performance world was changing. And this is very important. As a person in performance marketing, it had been my job for years to convince people that the performance numbers they were used to were no longer accurate. And the reasons for that came from changes out of VMware software as well as changes in the hardware. Now, the really important moments that occurred in 3.5 were large memory pages. Large memory pages gave better memory efficiency, increased the efficiency of the TLB. And if you know nothing at all about the TLB, just know that when it is efficient, virtual workloads run better. Also, at this time, AMD released their first generation of what we now call a hardware memory management unit. The hardware MMU, AMD branded as RVI, Rapid Virtualization Indexing. And RVI was a key technology for a class of workloads that VMware calls MMU intensive. These are workloads that run a lot of memory space, that swap out processes. They put incredible stress on the underlying platform. And AMD was in the forefront of providing a solution to this problem baked right into the hardware. And this means a lot for virtual workloads. Now at this point, this is going back to 2007 or so now, the CPU vendors are customizing code because they see the value of virtualization going forward. I'll also call out paravirtualization. Paravirtualization, I think we'll look back on as almost a fad or perhaps something that was a bridging technology that got us from old to new. Paravirtualization was very important back then. It was a mechanism by which you could recompile an operating system to tell it that it was now running on a hypervisor. How many of you today are running paravirtualized operating systems in your environment? We have 2 gentlemen in the back. That's it. I'll talk more about this in the longer performance talk, but the short version of this is Paravirt as an operating system is no longer needed because of the great changes in hardware. So jumping forward to vSphere. vSphere was both the reason for my great happiness and abject horror at having to go to work every day. When vSphere was launched, it was probably the biggest launch that VMware had ever done. And the hours that we were working to convince people that they now had a new platform that could run any application, the hours we worked were unbelievable. And it was worth it because I think we changed a lot of perceptions. The performance team, which had grown to a significant number of engineers by this point, 80 people or so, that were doing nothing but optimizing and qualifying the platform to make it run these banner workloads very, very well, really, really succeeded. And some of the changes they make, I will call out specifically a radical redesign that occurred in the storage stack. This was very important because up until this time, people rightfully believed that the VMware storage stack might not handle the most demanding I/O workloads. Now, I hope that to this day that no longer do you guys believe that at all. We worked very, very hard to get that message out of the industry and had some success, but I still every now and again hear people that are concerned about I/O. It is not something you should worry about anymore. VMXNet was improved. That's a paravirtualized driver. Paravirtualization in the drivers, good. Paravirtualization of the OS, bad. And it was at this point that Intel released a comparable functionality to what happened in AMD. They introduced a hardware memory management unit they called EPT. So this is how we were summarizing features back in the 4.0 time. Going back to 2.5, VMware used to use this strategy to get into accounts where they would say, you can virtualize your print servers, you can virtualize your DNS, you can virtualize your domain controllers. But when you get to databases, slow down. Hold off on those databases and let's work on those later. And the reason for that was implicitly we knew that databases were more of a challenge and had more overheads. That message way outlived its usefulness. And that message that we at VMware were delivering in 2007 echoed back to us and caused all kinds of problems in vSphere. But it is now gone. It was with vSphere that we demonstrated 365,000 IOPS on a single server that was done in just 3 VMs. and we had these great scalability improvements. Now, I've talked a lot about vSphere, but it's worth noting that there were incredible changes in the way the processors work too. So AMD V was the first support for hardware-assisted virtualization. That came out in the 2006 era, and it was about later that year, about a half year later, that Intel came out with its equivalent VT. Now, those first generations of those technology were actually slower than the software approach that VMware had been using for years. So the introduction of these were something that was avoided by as many customers as possible. Where VMware could choose to use its software approach and where customers were given the choice, it was often recommended to stay away from them. However, as time increased, that performance improved. You see, I say up there somewhat generally that AMD V and Intel VT eventually got 10 times faster. Well, we have latency charts that measured some of the critical instructions in that and showed that they got about 10x faster over the course of 2 years. So as time progressed, hardware assist became the way to go. I'll also call out another interesting point that happened that you all should remember with your older processors. We always believed in the performance team that a 4 meg cache was kind of a magic number. Now, the reason for this is that there's a certain amount of additional code that's executed in the virtualization of the I/O stack and the execution of the virtual workload. That additional code increases the working set. And when you increase the working set too much, the cache becomes inefficient. When the cache is inefficient, things slow down. As a result, with very small cached processors, a lot of the processors that were in the market in 2006 and 2007, even when they were running binary translation, the systems would slow down quite a bit. The cache would become inefficient, and there'd be problems. All of these were changed. Intel made improvements, AMD made improvements, and VMware made incredible improvements. Now, I want to contrast this against the trend in applications. Hardware's getting faster. VMware's getting faster. What's happening to operating systems? I think everyone has an innate understanding, even if they aren't computer scientists, in something called Amdahl's law, which basically says that any application can only scale to the point that it's entirely serialized. There's a certain amount of code that can only be run serially. Effectively, what this means is every application will max out at some number of cores. Now, the gentleman who was our chief performance architect, but now is a CTO, produced this graph for me a couple of years ago. Richard graphed out an individual application's ability to use multiple cores from 1990 all the way up to 2010. He did this on a logarithmic scale that shows Oracle at the top, the granddaddy of application scalability, theoretically maxing out around the ability to use 100 cores in the x86 market. Databases in general scale very well. They have a huge amount of concurrency, so we see great scaling from SQL Server as well. The thing I'm here to tell you is that it's entirely possible that every other application out there may max out around 10 cores. This is not to say that you can't put it on more cores, but that I don't believe that you're going to see an application run twice as fast on 32 cores over 16. In fact, with some applications, they actually go backwards. We call this reverse scaling. So that's the space right there where virtualization can assist performance, and vSphere's continual support is going to track this explosion of cores that's happening in hardware over time. So let me give you a few of the technical reasons why it's possible for an application to outperform native. The first is something called onloading. Now, I know that everyone probably understands the idea of offloading, which is taking some executing code and moving it to dedicated specialized hardware that takes work out of the CPU and pushes it off to specialized hardware. There's a similar thought, a similar concept called onloading, which means take some of the work that's running on some cores and put them on the same type of processor of which there are extras. So you can think of this as better using multiple cores that are available on a physical server. So it's possible, because of some of the multi-threaded drivers that exist in the VM kernel, to use more cores than were available in the physical environment. Scale out, as a result, allows us to get more access to cores and circumvent those limitations I put on the previous slide. Hardware assist has improved, has melted away overheads. And another thing that's very curious to us as well is the way that NUMA node isolation changes performance. If you run a virtual machine inside a single NUMA node, you change its cache access pattern. You guarantee all the access for that application is happening in one NUMA node, and you potentially can improve the efficiency of the cache. So let me sum this up. I mentioned that there have been tremendous changes that happened in the hardware environment, but it's incredible as much change that's occurred inside VMware as well, both features and evolutionary improvements in the way the code work. What happened over time is the overheads disappeared so much that we had in some cases the ability to exceed native, either through re-architecture or through single VM experiments. Now I'm going to bring Dave up to talk about applications, but first I want to point out perhaps a false positive in the space of beating native performance. This is the very first time I ever saw a physical workload that reported performance that is better than native. What this test is this is Microsoft's Jet Stress. Jet Stress is a tool that evaluates the storage performance. It evaluates your storage configuration and returns throughput and response time. So we did this test with our partners at HP at the time. And they ran the exact same configuration in a VM and in physical. And I'm going to point out two numbers there. One is the average disk seconds per read dropped by 2 milliseconds. The second is the total IOPS went up. So this is really confusing to us because I came back with this data and talked to my good friend in Outbound Performance, Kaushik Banerjee, who, if I may advertise my other talk, I am co-presenting with tomorrow. I went to Kaushik and said, Kaushik, it looks like we have this application running faster than native. And Kaushik gave me a verbal slapping around. He said, it's absolutely not possible. Listen, we're inserting more code in between what was an application and the hardware. If you add more code, how can it possibly run faster? And I didn't have a good answer for him. I pushed back and said, well, you should do the analysis. I'm in marketing, man. This is your responsibility. He actually never did that analysis, and this remained an open question for years. As it turns out, we saw this phenomena repeated in several cases where we ran Jet Stress, not just at HP, but at numerous partners. So is this running faster than native? My conclusion is I don't think that it is. I think what's probably happening here is this workload, which just sends IOs, read and writes, down to this configured storage, that the reads are going to uninitialized blocks. And they're coming back because ESX hasn't touched them yet. So it's just doing a memory access. It's never actually hitting the disk. However, this false positive, this configuration that led us to believe that we could beat native, started this idea in our head germinating that maybe actually there are applications where we can beat native. So let's get off the false positives and talk about the applications that do beat native.
Yep, thanks, Scott. So virtual outperforming physical, that's obviously a sensitive subject, and we raised a few eyebrows at VMware when Scott and I proposed this topic, and a lot of people told us we were crazy, and a lot of people told us not to do this session. It could be career suicide. And they actually said, Scott and Dave, this session could be an RGE, which is a resume-generating event. So we're going to show you the data, but this may be the last time you ever see us on stage representing anything from VMware.
Or maybe he'll be wearing a partner's badge next time like I am.
Very possible. We're going to start with IBM's WebSphere application server. And it's a good place for us to start for several reasons. One, there's lots of WebSphere applications out there. It's probably the most widely deployed commercial Java application server out there. There's a ton of web applications running on WebSphere, and because of that, there's a ton of x86 servers running WebSphere. So we have something that's representative of a lot of workloads out there. That's a good thing for us to start with. Second, it's a challenging workload, and that's true of Java in general. There's a perception out there that Java is difficult to virtualize. A lot of people have possibly held off on virtualizing the Java applications for various reasons. In fact, it can be done. It works great. There's a session here specifically on the best practices, but there's still some concern in the market and some perception that maybe Java is not a good candidate. So again, another good place for us to start. And the third reason is that, as you can see there, there's actually, how does this thing go? 3 performance studies. And IBM WebSphere Application Server is a nice talking point here because we have 3 separate performance studies done over 4 years. Each of these have been done together with one of our partners. They're all publicly available documents. And each performance study is on a successive version of ESX. So we can look at the improvements in performance on 2.5, 3.5, and 4. And we'll show you some incredible results. So with all of that, it's a good place for us to dig into some of the data. So 2006, circa 2006, we had a lot of customers who wanted to start consolidating web applications, and they were looking at using VMware as an approach to do that. And they started asking questions of both VMware and IBM like, What kind of performance can I expect when I consolidate these applications in a virtual machine? If I'm consolidating web apps, at that time we only supported 2 vCPUs in a VM. So customers were asking, should I use uniprocessor or SMP VMs for a web application? We didn't have that data. Now, how many VMs can I fit on a box? And what happens if I overcommit the CPU and memory? So VMware and IBM's performance teams set out to do this study. We used an IBM tool in this case, and in fact, in all the studies I'll show you, it's called DayTrader. And it's an IBM tool that is a J2E application that models an online stock brokerage. And WebSphere is commonly used in financial services, so they developed a tool that's representative of that kind of workload. And it tests end-to-end performance by pushing the CPUs to maximum utilization and then observing the throughput. So that may not be common in a customer's environment where the CPUs are running at 90% for the entire test or higher, but it's an excellent way for us to observe any virtualization overheads. So this test looked at a 4-way system and an 8-way system. We started with a physical baseline, which is that blue bar there, on a 4-way physical box. And then we ran that same test with 4 one-way VMs. So 4 aggregate CPUs, compared it to physical. And you can see the throughput came in at those 8 to 13% less. I think the average was about 10%. And then we ran that same test with 2 two-way VMs, and you can see the throughput was a little less. So in this case, the 2-way VMs were actually less efficient than the physical and the 1-way VMs. That same test was repeated on an 8-way system. With 8 one-way VMs, you can see we actually, for the first time, come in very close to native. The numbers were a little bit higher. And when we go to 4 two-way VMs, it's about 15% less throughput. So this is a publicly available document. If you really want to geek out and read historical WebSphere performance information, we defer you to the white paper. But the main point of that paper was, even as back as 2006, the statement was, this is a good platform for web apps. There is some loss in terms of throughput, but overall, performance is very solid. So this is a good data point for us to build on. So fast forward 3 years, the same test was repeated. Again, this is VMware and IBM doing this work together. You'll notice we're now on ESX 3.5. We're using a slightly newer version of WebSphere. And what we started to see in this testing was that if you look at the first blue bar, that's the physical system, and the green bars, while there was less throughput in the 1 and the 2 CPU cases, VMware started providing more throughput at 4, 8, and 12 CPUs. And this was puzzling because back in 2006, 4 one-way VMs were coming in at less throughput, and now we're coming in at more throughput here. And same with the 8-way cases. So we were curious about why that was. A lot of it has to do with some of the things Scott talked about in the performance improvements in ESX 3.5, some of the hardware assist that's built in, improvements in the scheduler, and all the stuff Scott talked about in the first section is starting to manifest itself in some of these results. So IBM actually went back and reran the tests on the physical system, and this time they pinned the CPUs on the physical OS, which basically tells the operating system to try to localize onto the same core at all times. And you'll notice that's the second bar, the purple bar. And if you look at the first 2 bars, the blue bars, you'll see that when you pin the CPUs on the physical system, performance improves by as much as 45%. And in that case, the physical system was outperforming all other cases. So we reran the tests pinning the CPUs on ESX, and you'll notice the 2 green bars here, that's pinned and unpinned and pinned. There really is no difference. So the ESX scheduler was already optimal. It showed no benefit from pinning the CPUs. And pinning the CPUs can boost performance in some cases. It can also lead to inefficient utilization in some cases. So we actually don't recommend it. So you're actually able to use ESX and be able to avoid the pinning. But the key takeaways here are this. 1, with 1 and 2 cores, we're still getting less throughput on VMware. 4, 8, and 12 cores, we're now consistently starting to provide more throughput than physical when we scale out on the box. So some significant improvements over the 2006 data. And for the first time, we're showing definitive numbers with higher throughput. Also, in the 2009 study, we did some single instance comparisons. What if I'm not running 8 one-way VMs on a box? What if I'm just running 1 VM with 1 vCPU against a physical box with 1 CPU? And what if I just compared a VM with 2 vCPUs to a physical box with 2 CPUs? And same thing in the 4-core case. So this is the data for comparing single instance, and at 1, 2, and 4, you can see the virtual is the green bars there. And back in that time frame, VMware was providing anywhere from 15 to 22% less throughput than a physical system. And those were expected results. That was about the expected overhead on all Tier 1 applications in that time frame. It ranged, but whether it was Exchange or SQL Server or SAP or whatever your workload of choice, back on the slide Scott showed, that was the expected overheads. So this is where things get really interesting. This is the latest and greatest data. This was done by HP and VMware earlier this year. And what we see here is that in the one CPU case, we're still a little bit less throughput, but we've gone from 18% less throughput to 5% less throughput here. But we'll notice in the 2 and the 4 CPU cases where previously we were delivering less throughput, 22 and 15 respectively, we're now comfortably delivering more throughput than the physical system. And this is just with a single instance comparison. So this is an absolutely phenomenal result. As Scott mentioned, when you're inserting a new piece of software in the stack, how can you possibly be faster than physical? And you'll notice up here we start to taper off a bit, and that tells us that there are certain sweet spot configurations for certain applications where we can make optimal use of CPU and cache efficiency on all of the new hardware, and where in certain configurations we can actually exceed physical performance by finding that sweet spot. And we've heard anecdotally from a lot of customers that when they've gone to virtualization, they've actually seen their application get faster, but customers probably haven't done this level of performance analysis. And here we can start to see some reasons why that might be. Just because there are these sweet spot configs where we make maximum benefit of hardware resources, cache efficiencies, and here we're clearly outperforming the physical system. So this was an encouraging result. I was in a session a couple hours ago. It was actually done by Siemens AG, and they were talking about some of their private cloud stuff that they'd done, and they had noticed as well when they moved applications onto virtualization that it was getting faster. And I don't know who the speaker was from Siemens, but he said, we tried to figure out why this was. And in addition to some of these benefits, what Siemens found is that when they moved applications onto the same box, all of the VMs on that box are now not having to go over the network to communicate with each other. They're communicating over a virtual switch at bus speeds. So in addition to being able to communicate at bus speeds and being able to use maximum cache efficiencies on the processors, there are some cases where this phenomenon is occurring. The same test here, the last slide on the WebSphere data, we did some testing with 4-way and 2-way systems. So this is a physical machine with 4 CPUs and a virtual machine with 4 vCPUs. And again, more throughput on the virtual case. This is an 8-way physical system, and this is 2 VMs with 4 vCPUs. And again, more throughput on the virtual piece. Down here, this is 2-way VMs, so a physical box with 2 cores compared to a virtual machine with 2 vCPUs, and a physical box with 4 cores and 2 2-way VMs. So you can see in many cases that we're actually outperforming on Java workloads. So these were great results. It's some very encouraging data that this phenomena is possible. It's a publicly available study, and it also says anyone who thinks that Java workloads can't be virtualized should take a look at this data. So that was our first case, WebSphere. We had a lot of good information. I'll switch gears now and go to Cognos Planning, and that's another IBM software product. Cognos is a big range of products. Planning is one product. So what I tell you here about Cognos Planning is not representative of every product in the Cognos family. But we got into this because we had some performance escalations coming in from the field, and we wanted to try to understand why those escalations in performance were occurring. And we reached out to IBM's Cognos Planning team. That's what my group at VMware does. We work with ISVs, and if necessary, we bring them into our lab. We help them do performance testing. So we reached out to IBM Cognos and said, hey, we've got some customers, some mutual customers with performance issues. Why don't we drag this into the labs and test it out and see what's going on here? So we did it at VMware's labs in Palo Alto. We did 2 rounds of testing, both on vSphere. And what we did with Cognos was we ran one set of tests on the older 5450 processors. I believe that's the Harpertown processor.
Correct.
And we repeated that same set of experiments on the latest Nehalem processors. And Scott gave a very thorough explanation of why we see such huge performance gains just by going to Nehalem. So a little bit about the test harness. I think the only thing I want to point out here is, again, much like WebSphere, we did a lot of different testing in the lab to find the sweet spot. We did some testing with a 2 CPU config, a 4 CPU, and an 8 CPU. We used a workload that was representative of a large Cognos production customer. We actually found this was the fastest configuration, but we had to run a lot more VMs on the box. So the 4 CPU VM actually gave us the best balance of performance and number of VMs to manage. And this ended up being the sweet spot for Cognos planning. And much like an Exchange infrastructure, for an example, we're looking at the job server in a Cognos environment. That's the performance-sensitive component. Much like if you're doing Exchange testing, you want to look at the mailbox server. With Cognos, we're looking at the planning system. The job server. So the 5450, the Harpertown data. Cognos is an analytics tool, a business intelligence tool for planning. It does a bunch of Cognos tasks. Here's the names of them. I won't get into the specifics. But we're looking at the time it takes to process 100 items. So the time it takes Cognos planning to do its analytics work. And if you're making business decisions and you're using analytics, you want the data as fast as possible. So in this case, the physical here, the blue, actually was able to complete those 100 items. The difference between physical and virtual was about 40%. So physical came in at 40% faster in this case on the 5450. Now, we repeated this same data, all else being equal. We just swapped out the processors and put it on a Nehalem system now. And when we ran the tests with EPT disabled, just on the Nehalem CPU, immediately performance improved by 20%. And that's actually what IBM tells us they see in the physical world as well. So if Cognos planning on a physical system goes to a new processor, they get a 20% boost as well. So we were right in line with physical. When we enabled EPT, performance improved a further 33%. So turning on EPT and going to the latest processor, we closed that 40% gap, and we're now almost identically comparable. Actually, the overall average is slightly faster on virtual now. So that's not bad. We were obviously very satisfied with that result. But where this gets interesting, and this is a different use case from the WebSphere data, but what we did on this box was we turned on hyperthreading. And when you turn on hyperthreading, we go from 8 physical cores to 16 logical cores on the box now. And instead of running 2 4-way VMs on the 8 physical cores, we ran 4 4-way VMs on the 16 logical cores. And in that particular instance, we were able to do the same amount of work 50% faster than the physical system. Now, why this is interesting is because, as Scott pointed out on one of his slides, there's a point where applications can no longer take advantage of more cores. It's typically around 8 CPUs. We see the same thing with Exchange. So if you're running a physical OS with Cognos planning, IBM actually will recommend to turn hyperthreading off because the application and the OS can't use those cores. So we can turn that on in a virtualized environment, put 4 VMs on the box, and do our analytics work and achieve a gain of 50%. So this also gives a little bit of a success story to hyperthreading, which has gotten a bit of a black eye in the past. Mm-hmm. But as you can see with this particular use case in Cognos planning, we were able to go from 40% slower to doing the same amount of work almost 50% faster. We closed the gap with Nehalem, and then we used hyperthreading to do more work on more VMs and do the same amount of work faster.
Actually, if I can add something about the hyperthreading, for every time I give a talk, a lot of techies come in. So let me give you a little bit of an explanation as to what's happening there. And I don't get paid by Intel, by the way, for saying this. The old version of hyperthreading was something that we were charged with selling when I was at Intel, and it was a difficult product to sell because what they were dealing with in the old NetBurst systems is a very, very long pipeline with many stages. And when you would context switch back between them, you would lose all the information in the pipeline. Those bubbles and stalls would cause all kinds of problems with efficiency. This is exacerbated in enterprise workloads where you have many, many threads running together and many hardware context switches. That was the old version of hyperthreading. And at that time, actually, it was quite common for VMware, in addition, to recommend that hyperthreading could be turned off. but it was very much an open question. Maybe sometimes it was good, maybe sometimes it was bad. Intel, like AMD as well, has done a great job of learning from its mistakes and making improvements. The new hyper-threading runs on a very different architecture with fewer stages, and they're saving information at those individual stages. So hardware context switches do not lose that information. Oops, excuse me. So let's talk about another application that's kind of interesting, and it's very relevant to just about all of VMware's customers, Microsoft Exchange. So this work right here was also done by our friend and colleague Kaushik Banerjee that I mentioned earlier. Kaushik and the two of us did this research on Exchange really based on an idea that Kaushik had just sitting around in his office thinking, that it was possible that we could beat these application scalability limitations by building a scale-out architecture on a single host. So instead of scaling out across multiple systems, we scale out across multiple virtual machines, but consolidate those. So the idea was supported by some documentation I'll talk about in a minute. And ultimately, we had quite a bit of success with it. We had so much success, in fact, that we had a press release that was probably one of the most well-known press releases Dave and I ever worked on, where we set a new record of number Exchange mailboxes on a single server. We ran 16,000 mailboxes on a single server, and this is on hardware that's now 3 years old. It was popular enough that Dave and I were lucky enough to go and present this at VMworld Europe, the inaugural VMworld Europe in Cannes. And I can recall the guilt we felt as the two of us were sitting on the French Riviera, sipping wine, thinking about poor Kaushik spending those late hours in the lab.
Very tough assignment.
So we, in our guilt, bought him a very nice bottle of scotch to bring him back and thank him for all the work he did. So why is it that we were able to beat native? Well, let me give you some guidance that was right out of Microsoft's recommendations. Dave talked about Cognos earlier, but Microsoft had on their TechNet pages solid recommendations about sizing. The first thing they said was, don't try to run more than 1,000 mailboxes per core. Now, I've shown a little graph here of number of cores in the bottom and number of mailboxes that can be supported, and drawn that limit, that black bar that goes up from the left to the right. Above that is outside of Microsoft's recommendations. Well, they had another recommendation. They said, don't bother running it on more than 8 cores. Now, again, this is not because Microsoft QA thought it was going to break, but they didn't want their customers buying these big, expensive systems when they had an application that they knew wouldn't yield value from those additional cores. Well, they actually had a third recommendation as well, which was that you need not size the memory above 5 megabytes per mailbox. This, of course, is an issue of cache efficiency. There's only so much memory that you can take advantage of before you're spending money on memory that's not yielding better performance. What this resulted in is a blue box that I've depicted up here, an area where Microsoft is very, very happy with the configuration, and they know their customers will love the Exchange deployment. So what's outside of that? Well, this red area where Microsoft says, simply don't do it. And also this yellow area where they say, oh, it'll work fine, but you're not getting the best value out of the memory. You're providing more memory than is needed. So where did this put users? Where did this put end customers? Well, commodity servers are the 16-core area, and they're getting larger by the day. I believe we're going to see Intel with a 96-core server in the next 18 months or so. So you can imagine the incredible pains that application developers are on to figure out a way to use cores. And as an aside, let me tell you, can applications use all these cores? I showed that application scalability earlier. I was asking our former chief performance architect, Richard McDougall, about that. And I said, Richard, why is it that these applications are unable to just scale and scale and scale and scale? He gave me a very simple answer that I really like. He said the only way a software company can get a piece of software to scale with that many cores is to spend millions and millions of dollars on it. This is the type of thing that Oracle has been doing for years on their database, and it's the type of thing that Microsoft is certainly doing with databases where they can afford to get that type of concurrency. But very, very few ISVs in the world even have that kind of money just to improve scalability. So I think by now you've heard us talk about scale out. You can probably guess how we were able to set this record. Well, let's look at the same graph again, and let me explain this pictorially. How about you instantiate a two-way virtual machine? Very, very simple. You use Exchange's scale-out capability to create 2 mailbox servers, each that are two-way. Each is two-way, using 2 cores, servicing a total of 2,000 mailboxes. It goes to 6,000 that way, breaking through this recommendation and still being in the blue zone, and up and up and up. So this means we could do 16,000 mailboxes in a server and be within Microsoft's guidance. Of course, it was very short after this that Microsoft revised their guidance and just said, don't run it on VMware. but they didn't change that sizing information for 2007. So now I think one of the things that we point out here is that we're not necessarily advocating that anyone should run 16,000 mailboxes on a server. I think as an exercise of risk mitigation, you don't want to have that many users dependent on a single physical server. But we're pointing out that by running what is twice as many mailboxes as had ever been done on a single server, that you're getting such better efficiency out of the host that it still benefits you and your consolidated infrastructure to run smaller VMs. Now, while we haven't repeated this scale-out experiment, VMware's outstanding performance team has done updates in their Tier 1 application group to show that you're getting great scalability in VMs of all sizes. They're rerunning tests that are 2-way and 4-way and scaling up on a variety of servers, showing that this chart and this efficiency is only getting better and better with time. Now, web servers, I think, are another fantastic workload. This is one of the few workloads where we have a very, very detailed analysis. Now, you heard me give a lot of theories, the best ideas as to why applications are beating native. This is one of them where the performance team pulled an engineer off of improving VMware's product and said, let's do a teardown of what's happening in the application, in the operating system, and in ESX itself to find out specifically what the components are that are causing scalability limitations. Well, let me first give a little overview of what's going on with web servers. I think everyone knows you're getting a lot of small I/O traffic coming in, possibly through one NIC. It's going into a large number of scale-out web processes that are farmed off servicing web pages one at a time. Those could be processes or threads, but they're all going to a common storage system. And through that, on the way to that common storage system, they're going through kernel locking parameters that exist in any operating system that control the order and access of write operations to these common files. That I/O goes out to the storage, bounces back up, and then a potentially very long message is sent back out another network. So what's happening? Well, we're getting a lot of processes swarming around that are all getting context switches between them. They're all accessing common files that are sharing kernel locking mechanisms provided by the operating system. And as a result, this application tends to be one of the worst scaling applications in the industry. So what did we find? Well, a great engineer named Srikanth Sethi that did a vTune analysis of this workload actually went down and looked at the code and found out, in fact, that there was OS locking contention that was hurting the web server's ability to scale with cores. Now, if you're interested in either this scalability test or any of the network IOC stuff, I recommend you go hunt down Srikanth. He is at the VMware booth, and he loves to talk about it. He's got a lot of depth. So what is the data he produced? Well, it was an analysis of Apache being tested by SpecWeb. He did a very simple experiment. He took the physical server, booted it with one core, and tested it against SpecWeb. Now, the number it turned up, you see, is the dark blue bar. It's scoring about 1,100 or so. Then he rebooted the same physical server, this time with 2 cores, and tested it a second time. This time it barely got to 2,000. So the scalability improved about 80%. But when he got to 3, 4, 5, and 6 cores, that blue bar has flattened out. This application is not returning any additional throughput by throwing more than 3 cores at it. In fact, if my memory serves me correctly, what Srikanth realized is that 8 cores performed 2.8 times faster than 1 core. That means 8 times more expensive, 8 times more power, but only less than 3 times as fast. Now, his experiment at the time in the virtual world used uniprocessor virtual machines. So what you see is in the pink bar, 1 virtual machine on the far left, and then 2 VMs, 3 VMs, 4 VMs. He scaled out the web farm the way you scale out real web farms, with a load balancer up front, farming off these IOs, farming off these web requests to the individual VMs. And it was through this process that he avoided that single OS locking contention and shattered the scalability limitations that existed. Now, Srikanth has done updates to this paper. This is the first time he published that scalability information. But Srikanth set a world record in web server performance with this architecture. But he was no longer using 1-way. He had done 2-way. And he has since done other tests with 4-way VMs. So he doesn't do anything beyond 4-way because of that fall off in performance. But 2-way VMs are okay for web server environments.
So the last example we have here is from the world of databases. And this is an example of a performance study that was completed earlier this year. And in this example, we're using a database technology that is called columnar database. And I won't get into the details of columnar other than to say there are a few advantages of columnar that align themselves well with virtualization. And columnar is also an excellent architecture for doing analytics-type workloads, scanning massive amounts of data in business analytics. But columnar is able to significantly reduce a lot of the I/O of a traditional database because it's able to read and write at the individual column level instead of having to read or write at an entire row level. And this is particularly useful for analytics, where in many cases we're doing a query where we only need data from one or two columns, and we can reduce I/O by as much as 90% in some cases. And anytime we reduce the I/O in virtualization, that's a good thing. You know, we reduce I/O and we free up more cycles for the CPU. So there's some benefits that align well. It's also what they call massively parallel. And this simply means that every time you add another node to the system, that node takes its own piece of the database. So if you've got 100 nodes, the database is spread across 100 nodes instead of a typical database where it's a single instance, a single, all the servers connecting to a single database where you can have single choke points. So it scales out extremely well using what's called MPP, and that aligns itself very well with how we can scale out virtual machines using cloning technology. And analytics is a very bursty workload. You're doing end-of-month or end-of-quarter processing, or in retail, you're sizing for some peak load over the Christmas season. So being able to scale up and scale down with virtualization and aligns well with an MPP architecture. So the reason we did this study is because VMware is now trying to attack analytics workloads. There's a huge opportunity out there to virtualize a lot of analytics servers. Actually, 50% of the databases in the world are being used for analytics, and it's also the fastest growing segment of the database market. As more and more companies turn to business intelligence and business analytics, there's more analytics databases out there. And I won't get into all of the use cases, but it's scanning massive amounts of data for patterns and all kinds of things where you need a certain type of database architecture. So the use case, I kind of just mentioned it, but typically when you're sizing an analytics system, you're sizing it for the peak, you know, just like any workload. When I used to size Exchange systems, we used to have to size it for like Monday at 9 a.m., you know, so that the storage subsystem could handle Monday at 9 a.m. with no performance problems. But then the rest of the time we weren't using the full resources of that system. It's the same in analytics, but it's a much bigger problem because you're buying iron to basically handle the peak over a 2-week Christmas season, and this iron can be in the millions and millions of dollars. These are not cheap solutions. With virtualization, we actually scale out very quickly to meet analytic workloads, and then we can simply either power down the virtual machines when we don't need them anymore and use that x86 architecture for other systems, or we can just delete the VMs entirely. So we don't have this problem where we have to buy a ton of huge iron and size it for a peak that we're only going to see periodically throughout the year. So in this example, you know, the whole session is about virtual machines beating physical machines. We wanted to go big on this one, and we wanted to take down the mighty Exadata. How many people are familiar with Oracle's Exadata? Dennis is familiar with Exadata. So we wanted to take down the previous record holder and do what's called a TPCH benchmark. The Transaction Processing Council is a third-party organization that hardware and software vendors can go to get their results certified. It basically says we're an independent body and we certify this result. It's not an easy thing to get a benchmark certified. There's a whole process we have to go through. We actually have to fly an auditor on site to sit there with us while we run all these tests to get their stamp of approval. And there's a period after the benchmark where VMware's competitors can challenge the results. If they find any way they can exploit the testing methodology, then they can challenge the results. So VMware has never had a fully audited TPC benchmark before. So we wanted to go after Exadata and the previous record holder in general at a 1 terabyte level, a 1 terabyte database. And we did it on commodity servers. We used the DL360G6. The boxes had 8 Nehalem processors and, I believe, 72 gigs of memory. And on each of these servers, we ran 2 virtual machines, Each virtual machine had 8 vCPU and 32 gig of RAM. So we had 80 virtual machines scaling out to basically load up this massive database and run this massive benchmark and see how we did. So analytics is challenging. Virtualization is typically not associated with analytics. Before we got into analytics, we wanted a big performance proof point. It's typically associated with big iron, like Exadata. And on April 10th, we set the world record for TPCH analytics databases at the 1 terabyte level. I mentioned it's the first time we've ever had a fully audited benchmark done on a VMware platform. And it positions us very well inside the analytics market. We were able to do this at 7.7 times better price performance than the previous record holder. So you can see the queries per hour we're doing on the VMware system compared to the previous record holders. And then the interesting data here is the price per query. So the price per query is 89 cents on the VMware platform because we're using commodity x86 servers. We scale out very effectively. So the price per query is significantly lower than the previous solutions. We just published a white paper. There's a benchmark report there. But this was a milestone achievement for us. We were able to do this with 37% fewer servers than the previous record holder had to do. Again, 7.7 times better price performance. So this was really a great achievement for our company and a great example of how we can use commodity hardware, how we can scale out very effectively and take down some of the biggest iron solutions in the market. So let's wrap up. There's some best practices. Again, this is not going to happen in every instance. We test hundreds of ISV applications in our labs, and we don't beat physical every single time. We've shown you some use cases of how this can happen, how you can do similar things, how you can find a sweet spot virtual machine that's going to give you the best possible performance. If absolute best possible response times and throughput are of interest to you, like in WebSphere where it's financial services and you're doing an online stock brokerage, you may want to consider doing some of these techniques. We've actually found that 2-way and 4-way VMs on the WebSphere data were the sweet spot. They actually performed better than VMs with more CPUs, and they actually performed better than their physical counterparts on those same configs. So in all the testing we've done, and if you have applications that you want to virtualize, do some experiments with different sized VMs, and it may benefit performance for you to take an application and split it into 2 or 3 chunks and use smaller VMs to maximize hardware and cache efficiencies and get that sweet spot configuration. You know, the benefit to using smaller VMs is that they're great for a virtual platform. You can vMotion a 2-way VM with 4 gigs of RAM a lot faster than you can a VM with 8 vCPU and 32 gig of RAM. So these small sweet spot VMs for performance are also great for vMotion, DRS, and HA. So find the sweet spot for your particular workload. Do some testing with different configs, some testing with scaling out to find the configuration that works best. The storage. I come from a storage background, and Scott has been on many a mission to customers all over the world where they've said there's perceived performance problems. A lot of people are doing a physical to virtual comparison before they migrate an application. They want to do some comparisons in performance. They run it on virtual. It sucks. It's 40% slower. We're not going to touch this Java workload. Something wrong here. A lot of times, I'd say greater than 70% of the cases, it's a storage problem. And either the storage is not configured properly, or the way they've done it in the physical world is according to these beautiful best practices, lots of fast drives and databases and logs isolated. And then on the virtual machine, it's on a shared VMFS data store with 800 other VMs. And we're trying to figure out why performance is not there. So we've had these escalations, and we've had to fly on site, and they've sworn up and down it's the same storage, and we got to the customer site, and it was the same storage. It was on Clarion. The same Clarion, but the virtual machine was on a SATA drive, a 1 terabyte SATA drive at 50 IOPS, and the physical machine was beautifully laid out across 100 15K RPM drives. So Scott's been the unfortunate recipient of many of these missions.
Yeah, at least one.
Where was your favorite?
Rural Arkansas was the one I had to go to overnight. But I did have one that sent me on a red eye to Boston, where when I walked in at 9 a.m., we had no idea what the problem was. And when we knocked out that storage problem by 1 p.m., I was able to make it over to Fenway Park for a game. So it could be worse. It could be a worse job.
So I'll leave you with finding sweet spot, finding the right configuration, and understanding storage. The storage layout is always very important. I think we all know that by now. But those are two areas where we definitely want you to pay attention to.
So we highlighted really three meta techniques of how you can beat performance. Sometimes one VM will run a little faster than it did in a native environment. Certainly by scaling out either on a single server, it'd be a second technique, or because vSphere is so adept at flexibly using a huge number of servers, you can find configurations that beat native. Dave and I think he was clear, don't mean to claim that now is an era where all applications run faster. But what we're showing you is that this old notion about performance has to fall apart is something that is no longer true. So what you should do in these new environments as you're considering new applications is you should pay very close attention to how things change in a consolidated environment. And you can lock in some of the performance that you've come to be comfortable with reservations. One of the things I've written about on my blog, for those of you that read it and for those of you that don't, is this idea of setting performance SLAs using reservations and limits. You can actually take any test, let's just pretend that it's Oracle being tested by Swingbench, test it against a full-size virtual machine, that is, it's got all of its resources, set limits to half the VM size, test again. Now that test at half performance becomes your SLA, because what you'll do is you'll flip the limits to reservations, bump the limits all the way up, put reservations where you tested it at, and now you can actually give your app owners a kind of SLA, right? Because you now know what the max performance is, because you tested, and what half performance is, what you guaranteed through reservations. Now, I'll warn you, this isn't truly an SLA, because the network or the storage could go haywire and could affect things. But it gets you very, very close and allows you to go into consolidated environments with a near guarantee about performance. So play around with reservations and pay attention to applications that use a lot of memory in fixed memory sizes like Java or the Oracle SGA. Those definitely merit a little attention for reservations.
I think that's one of the most important Java best practices as well. Is there's certain workloads where it becomes extremely important to reserve CPU and memory. Java apps happen to be one of those. My colleague works is doing the Java best practices session, and that's one of the ones that he preaches. So depending on the workloads, they may not just work well when memory is shared with page sharing, with that kind of thing. So depending on the workload, this can be very important.
So those of you that are interested in Java, definitely go check out Justin Murray's talk. He's a charming and intelligent Irishman, and his talk is already one of the top 3 most popular here. It's going to be repeated tomorrow. So go check it out. The last comment I'll give, just a general best practice, don't pay too much attention to OS level stats. In the old days, we used to just say ignore them, ignore them, and ignore them. But it seems that those OS level stats are getting more and more accurate over time. They still don't have visibility into what's happening in the time sharing in the hypervisor. So you can use them as kind of a thumb suck and get an idea of what's happening. But when you're really troubleshooting performance problems or managing capacity, you want to use VMware's tools. Follow the best practices. Those are documented by the ISVs. Definitely stick to those. Perform those single VM tests. If you are that speed freak that needs the most out of your environment, you're going to run these tests yourself. You have to. If you don't have the time and you just want to get about as close as possible, our general guidance to you is probably a 2-way VM is probably the right configuration. In some of the larger applications, maybe 4-way. Scale out comfortably. We have never seen any issues that we know of with vSphere, where adding more VMs is going to impact performance. It's pretty impressive, the linear scalability we've seen with versions of vSphere going back to when it was called VI3. And pay attention to the primary resource areas to correct bottlenecks. So for most of the time, set it and forget it. You don't have to worry about it. When every cycle counts, follow these steps, as we mentioned earlier. I won't go through them. And note that we did not include data on vSphere 4.1. This topic was created and accepted and approved through the VMworld system before 4.1 launched. But I'll call out a couple of features that may actually improve things. There were some scheduler improvements around hyperthreading that could squeeze out even more cycles in your environment. And there's a new feature called, wide NUMA VM enhancements that does a better job of placing big VMs on NUMA nodes. Thanks, everyone, for coming. I hope that you will fill out these with very good reviews, hopefully. And if you have questions, please come up. Dave and I are going to stay around for a little while. I saw your hand in the back. You'll be the first one we answer.
Thank you for coming.
Everyone.